Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of space, where distances are measured in millions of kilometers and communication delays stretch across minutes or hours, humanity faces a fundamental challenge. Traditional radio waves, the backbone of our current space, communication systems, travel at the speed of light but still require precious time to bridge the cosmic void. A signal from Mars takes between 4 and 24 minutes to reach Earth, depending on planetary alignment. This delay becomes a critical limitation as we venture deeper into the solar system and beyond. The solution may lie in one of physics' most counterintuitive phenomena, quantum entanglement. Albert Einstein famously called it spooky action at sea, a distance, describing how two particles can become mysteriously connected, instantly affecting each other regardless of the distance separating them. This quantum mechanical property, once considered purely theoretical, now represents the foundation of what scientists call quantum communication. At its core, quantum communication relies on the principles of quantum mechanics, where information is encoded in quantum states rather than classical bits. Unlike traditional digital communication that uses ones and zeros, quantum systems employ quantum bits, or qubits, which can exist in multiple states simultaneously through a property called superposition. When two particles become entangled, measuring the state of one particle instantly determines the state of its partner, no matter how far apart they are. This phenomenon offers revolutionary possibilities for space exploration. Current deep space missions rely on the Deep Space Network, a collection of massive radio antennas operated by NASA across 3 continents. These systems, while remarkably sophisticated, face inherent limitations. Signal strength decreases with the square of distance, requiring increasingly powerful transmitters and receivers for missions venturing to the outer planets. The Voyager 1 spacecraft, now over 14 billion miles from Earth, transmits data at a rate of just 160 bits per second. Quantum communication promises to transcend these classical limitations. In theory, quantum entangled particles could enable instantaneous information transfer across any distance, fundamentally changing how we communicate with spacecraft, rovers, and future human settlements throughout the solar system. The implications extend beyond simple data transmission. Quantum networks could enable real-time control of robotic missions, seamless coordination between multiple spacecraft, and unprecedented levels of data security through quantum cryptography. Recent advances in quantum technology have moved these concepts from theoretical physics into practical engineering. Scientists have successfully demonstrated quantum entanglement over increasingly large distances, from laboratory benches to satellite-based experiments spanning thousands of kilometers. China's quantum science satellite, launched in 2016, achieved quantum entanglement between ground stations separated by 1,200 kilometers, proving that quantum effects can survive in the harsh environment of space. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The European Space Agency has initiated the Quantum Internet Alliance, aiming to develop space-based quantum communication networks within the next decade. Similarly, NASA has begun investigating quantum communication technologies for future Mars missions, recognizing the potential to revolutionize interplanetary exploration. These initiatives represent the first steps toward a quantum internet spanning the solar system. The technical challenges are immense. Quantum states are extraordinarily fragile, easily disrupted by environmental interference, temperature fluctuations, and cosmic radiation. Maintaining quantum entanglement across the vacuum of space, while theoretically possible, requires unprecedented precision in engineering and control systems. Scientists must overcome decoherence, the process by which quantum systems lose their quantum properties when they interact with their environment. Despite these obstacles, the potential rewards justify the extraordinary effort. Quantum communication could enable humanity to maintain real-time connections with colonies on Mars, coordinate complex multi-spacecraft missions to the outer planets, and establish secure communication networks that are fundamentally unhackable due to the laws of quantum mechanics. As we stand on the threshold of becoming a multi-planetary species, quantum communication may prove to be the key technology that keeps our civilization connected across the cosmos. Quantum entanglement operates through mechanisms that challenge our everyday understanding of reality. When two particles become entangled, their quantum states become inextricably linked, forming what physicists call a quantum system. This connection persists regardless of physical separation, creating correlations that cannot be explained by classical physics. The measurement of one particle's property instantaneously affects the measurement outcomes of its entangled partner, a phenomenon that has been verified through countless experiments since the 1970s. The process begins with creating entangled particle pairs, typically photons or electrons, using specialized equipment such as nonlinear crystals or quantum dots. These particles share quantum properties like spin, polarization, or energy states. When scientists measure the spin of one particle and find it rotating clockwise, they know with absolute certainty that its entangled partner will be rotating counterclockwise, even if separated by vast distances. This correlation appears to violate the speed of light limitation, but quantum mechanics reveals that no information actually travels between the particles during measurement. Ground-based quantum communication has achieved remarkable milestones in recent years. Researchers at the University of Science and Technology of China successfully transmitted quantum-encrypted messages over fiber optic cables spanning more than 2,000 kilometers. The system maintained quantum entanglement integrity across this distance, demonstrating the feasibility of large-scale quantum networks. These terrestrial experiments provide crucial insights for space-based applications, where distances and environmental challenges increase exponentially. Space presents unique advantages and obstacles for quantum communication systems. The vacuum of space eliminates atmospheric interference that plagues ground-based quantum networks, potentially allowing for cleaner quantum state transmission. However, cosmic radiation, temperature extremes, and the mechanical stresses of launch and orbital operations pose significant threats to delicate quantum systems. Photons traveling through space encounter minimal interference, making them ideal carriers for quantum information. But generating and maintaining entangled photon pairs in space requires robust, miniaturized equipment capable of operating in harsh conditions. China's mightiest quantum satellite, launched in 2016, represents humanity's first successful space-based quantum communication platform. Named after the ancient Chinese philosopher, this 590-kilogram satellite operates at an altitude of 500 kilometers, establishing quantum communication links with ground stations across China and Europe. The satellite generates entangled photon pairs using a non-linear crystal pumped by a laser system, then transmits these photons to ground-based telescopes for quantum key distribution experiments. The Multiverse mission achieved several groundbreaking milestones. It successfully distributed quantum encryption keys between Beijing and Vienna, spanning 7,500 kilometers, creating the world's first intercontinental quantum communication network. The satellite maintained quantum entanglement over distances exceeding 1,200 kilometers, surpassing all previous records. Most significantly, it demonstrated quantum teleportation from ground to satellite, transferring quantum states across 600 kilometers of space. Technical requirements for space-based quantum networks demand extraordinary precision. Quantum states exist for microseconds before decoherence destroys their quantum properties, requiring ultra-stable laser systems, precise timing mechanisms, and sophisticated error correction protocols. Satellites must maintain pointing accuracy measured in microradians to ensure photons reach their intended ground stations. Temperature control systems must keep quantum components within millikelvin ranges to preserve entanglement properties. The European Space Agency's Quantum Technologies flagship program aims to deploy a constellation of quantum communication satellites by 2030. These spacecraft will feature advanced quantum memory systems capable of storing quantum states for extended periods, enabling more flexible communication protocols. The satellites will incorporate quantum repeaters, devices that can extend quantum communication range by refreshing quantum states along transmission paths without destroying the quantum information. NASA's Quantum Communications and Sensing program investigates applications beyond communication, exploring quantum sensors for gravitational wave detection and precision navigation. Quantum-enhanced sensors could detect minute gravitational variations, enabling spacecraft to navigate using gravitational maps of the solar system rather than relying solely on radio beacons from Earth. Commercial companies are joining government agencies in quantum space ventures. Companies like Quantum Space and Spectral are developing miniaturized quantum communication payloads for small satellites, reducing costs and increasing deployment flexibility. These efforts could establish quantum communication services for commercial space missions, scientific instruments, and future lunar or Martian settlements. The convergence of quantum physics and space technology represents a paradigm shift in how humanity will communicate across cosmic distances, setting the foundation for truly interplanetary quantum networks. The Messius quantum satellite mission transformed theoretical quantum communication into tangible reality, establishing the first operational quantum network spanning continents. Operating from its sun-synchronous orbit, Messius generates approximately 6 million entangled photon pairs per second using a beta-barium borate crystal excited by a 405 nanometer laser. These photons travel through space to ground stations equipped with 1.2-meter telescopes capable of detecting individual photons arriving at rates of several thousand per second. The mission's most remarkable achievement occurred in 2017 when researchers successfully demonstrated quantum key distribution between ground stations in China and Austria. The process involved generating entangled photon pairs aboard the satellite, transmitting one photon to each ground station, and using the quantum correlations to create cryptographic keys that are theoretically unbreakable. The experiment achieved key generation rates of 1.1 kilobits per second over 7,500 kilometers, representing a million-fold improvement in distance over previous ground-based quantum communication attempts. Quantum teleportation experiments conducted by Messius pushed the boundaries of quantum physics applications. The satellite received quantum states from a ground station in Tibet and successfully teleported these states to another location 1,400 kilometers away. This process doesn't involve moving particles through space, but rather transferring quantum information by exploiting entanglement correlations. The fidelity of quantum state transfer exceeded 80%, surpassing the classical threshold and confirming genuine quantum teleportation across unprecedented distances. The European Space Agency's Quantum Communication Infrastructure program represents the next evolutionary step in space-based quantum networks. The initiative plans to deploy a constellation of 12 quantum communication satellites by 2027, creating a European quantum internet spanning from Scandinavia to Mediterranean regions. These satellites will feature advanced quantum memory systems using rare earth-doped crystals, capable of storing quantum states for milliseconds, allowing for more sophisticated communication protocols and network architectures. European researchers have developed quantum frequency conversion techniques that allow quantum information encoded in near-infrared photons to be converted to telecommunication wavelengths compatible with existing fiber optic infrastructure. This breakthrough enables seamless integration between space-based quantum networks and terrestrial quantum communication systems, creating hybrid networks spanning both space and ground-based components. NASA's Artemis program includes provisions for quantum communication systems on lunar missions. The Lunar Gateway space station will serve as a testbed for quantum communication technologies, establishing quantum links between Earth and lunar orbit. These experiments will investigate how quantum systems perform in the unique electromagnetic environment around the Moon, where Earth's magnetosphere provides reduced protection from cosmic radiation. The agency's Deep Space Optical Communications experiment, launched aboard the Psyche mission in 2023, demonstrates advanced laser communication systems that will eventually incorporate quantum protocols. While currently focused on classical optical communication, the mission provides crucial infrastructure and experience for future quantum communication systems operating in deep space environments. Commercial ventures are accelerating quantum space development through innovative approaches and reduced costs. Spectral, a Singapore-based company, has developed compact quantum key distribution payloads weighing less than 10 kilograms, suitable for integration into small satellites or CubeSats. Their technology uses silicon photonics to miniaturize quantum optical components, reducing power consumption and increasing reliability in space environments. Quantum Space, founded by former NASA Administrator Jim Bridenstine, focuses on quantum sensors for space applications, developing quantum gravimeters and quantum clocks for precision navigation and scientific measurements. Their quantum sensors could detect gravitational anomalies on planetary bodies, enabling detailed mapping of subsurface structures on Mars or asteroids. Recent breakthrough experiments have demonstrated room temperature quantum memory systems, using diamond nitrogen vacancy centers, potentially eliminating the need for complex cooling systems in space-based quantum devices. Researchers at Harvard University achieved quantum memory storage times exceeding 1 second at room temperature, representing a 100-fold improvement over previous systems requiring cryogenic cooling. Australian researchers successfully demonstrated quantum communication through atmospheric turbulence using adaptive optic systems that could be adapted for satellite communications. Their experiments showed that quantum states can be preserved even when photons pass through atmospheric distortions, equivalent to those encountered during satellite-to-ground transmissions. These missions and experiments collectively demonstrate that space-based quantum communication has transitioned from theoretical possibility to engineering reality. The convergence of multiple national space agencies, commercial companies, and research institutions creates a robust foundation for developing comprehensive quantum communication networks that will support humanity's expansion throughout the solar system. Quantum decoherence represents the most formidable obstacle facing space-based quantum communication systems. In the unforgiving environment of space, quantum states face constant threats from cosmic radiation, thermal fluctuations, and electromagnetic interference. Decoherence occurs when quantum systems interact with their environment, causing the delicate superposition states essential for quantum communication to collapse into classical states. Space-based quantum systems must maintain coherence times measured in microseconds, while operating for years in conditions that would destroy conventional quantum states within nanoseconds. Engineers have developed sophisticated isolation techniques to combat decoherence. Quantum systems aboard satellites employ multiple layers of electromagnetic shielding using superconducting materials and mu-metal enclosures to create electromagnetic field-free zones around sensitive quantum components. Vibration isolation systems using magnetic levitation and active damping protect quantum states from mechanical disturbances caused by satellite attitude adjustments, thermal expansion, and orbital mechanics. Cosmic radiation poses an additional challenge that doesn't exist in terrestrial quantum systems. High-energy particles from solar wind and galactic cosmic rays can disrupt quantum states and damage sensitive electronics. Radiation-hardened quantum devices incorporate specialized error detection and correction protocols that can identify and compensate for radiation-induced errors without destroying the quantum information being processed. Silicon carbide and diamond-based quantum systems show promise for space applications due to their inherent radiation resistance compared to traditional semiconductor quantum devices. Precision pointing and tracking requirements for space-based quantum communication demand unprecedented accuracy. Quantum communication links between satellites and ground stations require beam divergence angles measured in microradians to ensure photons reach their intended destinations. A typical quantum satellite operating at 500 kilometers altitude must maintain pointing accuracy better than 1 microradian to successfully establish quantum links with ground-based telescopes measuring 1.2 meters in diameter. Advanced attitude control systems employ star trackers, gyroscopes, and reaction wheels, operating in closed-loop feedback configurations to achieve this precision. Fine-pointing mirrors controlled by piezoelectric actuators provide final beam steering adjustments, compensating for satellite vibrations and thermal drifts. These systems must operate continuously for years while maintaining quantum-grade precision, requiring redundant components and sophisticated fault-tolerance mechanisms. Quantum error correction protocols, specifically designed for space applications, address the unique error patterns encountered in orbital environments. Unlike terrestrial quantum systems where errors occur randomly, space-based systems experience correlated errors from cosmic ray events, thermal cycling, and magnetic field variations. Quantum error correction codes such as surface codes and color codes provide protection against these correlated errors while minimizing the overhead of additional qubits required for error correction. The integration of quantum communication systems with existing space communication infrastructure presents complex engineering challenges. Quantum satellites must maintain compatibility with traditional radio frequency communication systems for spacecraft telemetry, command, and control functions. Hybrid communication architectures incorporate both quantum and classical communication channels, allowing seamless fallback to conventional systems when quantum links experience disruptions. Timing synchronization between quantum communication nodes requires atomic clock precision, better than 1 nanosecond, to ensure proper quantum protocol execution. Space-qualified atomic clocks using rubidium or cesium standards provide this precision, but must be calibrated regularly against ground-based atomic time standards. Global navigation satellite system signals provide additional timing references, but quantum communication systems must account for relativistic effects that cause time dilation differences between satellite and ground-based clocks. Thermal management. Systems for space-based quantum devices must maintain stable temperatures while operating in the extreme thermal environment of space. Spacecraft experience temperature swings from -100 degrees Celsius in Earth's shadow to +100 degrees Celsius in direct sunlight. Quantum systems require temperature stability better than 1 millikelvin for optimal performance, necessitating sophisticated thermal control systems using heat pipes, radiators, and active cooling elements. Miniaturization of quantum systems for space deployment requires innovative packaging techniques that maintain quantum performance while reducing size, weight, and power consumption. Advances in integrated photonics enable quantum optical components to be fabricated on single chips, reducing the complexity and improving the reliability of space-based quantum systems. These integrated quantum photonic devices can withstand the launch environment while providing the functionality of room-sized laboratory quantum systems. Ground station requirements for quantum communication networks demand specialized facilities. With quantum-grade optical systems, ultra-low noise detectors, and sophisticated signal processing capabilities, these ground stations must be distributed globally to maintain continuous coverage of quantum satellites, requiring international cooperation and standardization of quantum communication protocols. The successful resolution of these technical challenges will enable the deployment of robust, reliable quantum communication networks that can operate in the harsh environment of space while providing the unprecedented capabilities that quantum physics promises for interplanetary communication. The future of space-based quantum communication extends far beyond current experimental demonstrations, promising to revolutionize human civilization's expansion throughout the solar system. Within the next 2 decades, quantum communication networks will likely span from Earth to the Moon, Mars, and eventually the outer planets, creating an interplanetary internet that connects human settlements across astronomical distances with unprecedented security and potentially instantaneous information transfer. Mars colonization efforts will benefit enormously from quantum communication infrastructure. Current communication delays between Earth and Mars range from 4 to 24 minutes, depending on planetary positions, making real-time coordination impossible. Quantum communication could eliminate these delays entirely, enabling immediate collaboration between Earth-based mission control and Martian colonists. This capability will prove crucial for emergency response, medical consultations, scientific research coordination, and maintaining psychological connections between Earth and Mars populations. The technical architecture of an interplanetary quantum network will require quantum repeaters stationed throughout the solar system. These devices will refresh quantum states along transmission paths, extending the range of quantum communication beyond current limitations. Quantum repeaters positioned at Lagrange points, where gravitational forces from multiple celestial bodies create stable orbital positions, could serve as permanent quantum communication hubs connecting various planetary systems. Advanced quantum satellites deployed in constellation formations around each planet will create local quantum networks that connect to the broader interplanetary system. Mars will likely host a network of 12 to 20 quantum communication satellites in various orbital configurations, providing redundant coverage for surface settlements, orbital facilities, and transit vehicles. These constellations will employ quantum mesh networking protocols that automatically route quantum information through multiple paths, ensuring communication reliability even if individual satellites fail. The asteroid belt presents unique opportunities for quantum communication infrastructure. Mining operations on asteroids will require robust communication systems for coordinating automated mining equipment, managing supply chains, and ensuring crew safety on human-operated facilities. Quantum communication networks could enable centralized control of distributed mining operations across thousands of asteroids, optimizing resource extraction and transportation throughout the solar system. Jupiter's moons represent the next frontier for quantum communication expansion. Europa, Ganymede, Callisto, and Io will likely host scientific research stations and eventual settlements requiring communication with Earth and other solar system locations. The intense radiation environment around Jupiter poses additional challenges for quantum systems, but also opportunities for studying how quantum states behave under extreme conditions that don't exist elsewhere in the solar system. Quantum communication will enable new forms of distributed computing across interplanetary distances. Complex scientific simulations, artificial intelligence processing, and data analysis tasks could be distributed across quantum-connected facilities on multiple planets, creating a solar system-wide supercomputing network. This capability will accelerate scientific discovery, enable sophisticated modeling of planetary systems, and support advanced artificial intelligence applications for space exploration. The economic implications of interplanetary quantum networks are profound. Secure quantum communication will enable trusted financial transactions between planetary settlements, supporting the development of a truly interplanetary economy. Digital currencies based on quantum cryptography could facilitate trade between Earth, Mars, and other settlements, while preventing fraud and ensuring transaction integrity across interplanetary distances. Long-term implications extend to humanity's expansion beyond the solar system. Quantum communication networks established within our solar system will serve as the foundation for eventually connecting with interstellar missions and potential settlements around nearby stars. While quantum entanglement doesn't solve the fundamental challenge of interstellar distances, the infrastructure and expertise developed for solar system quantum networks will be essential for establishing communication with humanity's first interstellar colonies. The timeline for these developments suggests that lunar quantum communication links will be operational by 2030, Mars quantum networks by 2035, and outer planet connections by 2040. This timeline depends on continued technological advancement, international cooperation, and sustained investment in quantum space technologies. Educational and cultural exchange will be transformed by quantum communication networks. Students on Mars could attend lectures at Earth universities in real time. Scientists could conduct collaborative research across planetary boundaries, and families separated by interplanetary distances could maintain meaningful connections through instantaneous communication. As humanity becomes a truly multi-planetary species, quantum communication networks will serve as the nervous system of our interplanetary civilization, enabling the coordination, cooperation, and cultural unity necessary for humanity to thrive. Throughout the solar system, and eventually among the stars, the quantum revolution in space communication represents not just a technological advancement, but a fundamental enabler of humanity's cosmic destiny.